Hey everybody, I'd love to introduce Adrian Duran from, I guess, Caltech now. It's a pleasure to have him because he's been working a lot on algorithms for discovery of causal drivers of complex phenomena, in particular in physics. Welcome, Adrian.
Thank you. So I hope that you find this talk interesting. I'm going to be talking about causal inference in general. It's going to be a bit conceptual first, and then I'll discuss some of the tools that we have developed in my group for causal inference. So let me first start. I want to acknowledge the people in my group. So in general, what we do, we work in problems related to aerospace. So that's my background. And also in developing tools for aerospace applications. So if I can divide like the two thrusts that we have in the group. So on one hand, we will have methods for causal learning, just model discovery or control. The key here is that we typically are interested in chaotic systems, systems that are very highly nonlinear and highly dimensional. And we use different tools. Sometimes we use information theoretic analysis to understand the relationship in the system, and also causal inference. That is what I'm going to be talking about today here. And that's also typically based on information theory. Then we have more applied approach in which we care about things that fly, typically like an aircraft, rockets, drones. And we try to obtain reduced order models for these systems. We try to understand also the physics, like some physical insights, what are the different quantities of interest and how they relate to each other. And we also develop a lot of closure models for these cases. So sometimes there is a transfer of knowledge between like the methods to generating actual closure models. And typically these models are for computational fluid dynamics. But today I'm going to talk more about the part of the methods, but I would also show some small applications to turbulent flows and fluid mechanics. Okay. So I wanted also to acknowledge the people who has been working on the causal inference part of the work. Noli, Alvaro, Gonzalo, and also Timur, and acknowledge the funding from NSF and DOE. Okay, so causality in science actually is a key tool in many different fields. So it goes from climate, ecology, economics, neuroscience. The particular field I'm interested in is fluid dynamics. That curiously, there is not so much in causal inference. So that's how I got engaged, like learning from other fields and try to bring that knowledge to the field of fluid dynamics, and also try to contribute to the field of causal inference by some improvements in the way we approach the problem and the methods. But it has in other disciplines, this is something that has been very well established. One of the first places where causal inference was established was in economic sciences. And as a curiosity, there are 2 Nobel Prizes that they were somehow connected to causality for economic sciences or social sciences. One is Granger. So he introduced the Granger causality. So Granger causality was introduced like very early 70s, but then Granger himself got the Nobel Prize later in 2003. And the other contribution is more recent, comes from what is called natural experiments. This was the Nobel Prize in 2021. So these are 3 people from MIT, UC Berkeley, and Stanford. They also contributed to methods for causal inference and applied to social sciences. Now, the key question here, or usually typically the challenge for causal inference is what is causality? I use this video that I want to credit to Laura Prescott, in which we have this intuitive idea that causality is a sequence of events. So we go from one event that it would be the cause of the next one, and then the next one, and then the next one, and there's all this change. And we want to understand that. And this is a fair definition in a way of, or like a conceptual definition of causality, although there are some issues with that, and I'll discuss this a bit later. But generally, what we want is something like this. So this would be like a problem statement. Typically, we have a system. That system is high dimensional. There are many variables. The system may be chaotic, very unpredictable. But we care about some quantities of interest. That's what I'm representing here by this Q. So Q is a quantity of interest. And I have maybe this example, I have 5, Q1 and Q5. I might have other variables that are listed here from Q6 to Qn, and n could be very large. Could be, for example, 1,000 or millions or billions, it depends on the problem. But the idea is that we want to create a map that is connecting these variables, how they affect each other. Like I know, according to this graph, that Q2 is affecting Q1 and Q3, but not the other way around. And this is something that we want to discover. We want to know these arrows. Ideally, it's not only the direction of influence between one variable and the other, we also want to know the strength. So how strong is this connection? And we also need to be aware that there might be other variables that we cannot measure, we don't have, or we don't care, but they might have an impact also on the variables we care about. And it would be actually a good property of our method that we are able to also extract that information from the system. So general problem is time, and now the question is, how do we do this? And that's where there are different methods for causal inference to quantify this. So let's imagine that I have a method to obtain that graph. Now, what do I do with that? So obviously, depending on the interest of different people, they do different things. I can tell you a bit of what we care about in my group. So we care about three things. One is physical insight. So physical insight means I have this is an example of one of the simulations that we have. This is we solved the Navier-Stokes equation. So this is a flow. This is a simulation in which the direction of flow is changing. But you can see this is a system that looks very complicated. What I'm visualizing here is the magnitude of the velocity. It's very chaotic. There are many details, different scales. But we define some quantities of interest in this problem. And this is what I'm representing here with this schematic, quantity from 1 to 5. And I would like to create this causality map. From one variable to another, how do they affect each other? So according to this map, the variable Q1 is affecting almost all of the other variables in the future, and the variable Q2 has no impact whatsoever. So now I know that the variable Q2 is not relevant for the future of the other variables that I care about. And this is kind of the idea. We can try to understand the physical meaning of that, and what are the variables that are important and how they relate. Another application, it'll come actually from simplifying the system through a reduced order model. This system might have millions of degrees of freedom. Maybe I want to create a system that is also useful to make predictions, or as a surrogate model to compute some sensitivities. And that's what we do, what we call the causality preserving models. So here I'm sketching an autoencoder using CNNs, but in general, it could be any model. But imagine I want to create a reduced order model to predict this flow that will come through this first layer, and then I'll get some predictions of other quantities I care about. But the key here is that we don't want to just construct this model. What we want is that if we compute the causal relationships from this model, they match the causal relationships of our quantities of interest in the full system. And that's what it is causality preserving. That's what we would like. And there are many advantages of doing that. In terms of then later, if suddenly my model sees data that is out of the training set, like extrapolation, it will behave much better if the causal relationships are consistent. Or if I want to compute sensitivities and introduce perturbations in my model, it would be much better that the causal relationships are the ones that you will find in the actual systems. Otherwise, the answer could be misleading that you get. And the last step is actually about manipulating the system itself, and is this causality-driven control. I'm showing here a simulation of an aircraft that we do. So in this case, we could move to more complex cases. I imagine that I look close to the wind. So I'm going to show you now another inset. So this is the wind, and this is a simulation that we have, and we are just visualizing on average the flow, the trajectory of the flow across the wind. So in these cases, we want to control when you have some actuators and some sensors. In this case, we want to improve the efficiency of the wind. And the idea here is similar to the reduced order modeling. We don't want just to create this reduced order model to predict. We want to create this reduced order model to control the system. And in that sense, causality is very important, because there might be that two quantities are correlated, but that they are correlated doesn't mean that by modifying one, I'm going to affect the other. However, causality comes like a more natural way of doing that. So if two things are causal, one to each other, then I know that if I manipulate one, I can control the other one. So in this case, we want to, again, make sure that the causal structure of the system is as it should be, is faithful to the full system. And then the control that we obtain computationally, we then implement that experimentally, it want to be effective. So 3 examples of that.
So
if you're
what does success look like? Is it, I mean, I'm noticing things like, looks like transferability from like extrapolability of a given model because it's robust in some way. I'm seeing interventional kind of definition of success. What do you, these, what do you have in mind?
So depending on the case, they will, the problem, you might define what is your metric of success. And probably depending on your metric of success, it might be that the causal inference tool that you need to use is different. It's the way you extract this skeleton in a way. But that's a very good question. Yeah, you can pose the problem, say, okay, this is my metric for success. This is how I would say that my reducer model works. And then from there, from those properties that you want, you can try to pinpoint what is the causal method for inference that will give me those properties. I would say that maybe there's no general answer. It's more that depending on what exactly you define success. Yeah, but that's important, and it's not a trivial question actually. So you need to look into that carefully. Okay. Many of these ideas about using causality, in the case of our group, we use information theory. So these are, you can take a look at this paper. Many of these ideas are there about causality and control, particularly on chaotic dynamical systems. So this is what I'm going to talk about. First, I'm going to try to discuss a bit more about what is causality, different ways of understanding causality, and then what are the challenges. So if now I want to develop a method for causal inference, what are the problems I need to face? I'll discuss briefly other methods for causal inference, and then I'll talk about our particular method that we develop to tackle the problems we care about, that is based on separating causality in synergistic, unique, and redundant components. And I'll show a few applications, and I would also like to discuss the limitations of the method of how things might break at some point. But if we go to the first question, what is causality? So there is this, I'm quoting Judea Pearl, and at a very high level, causality is just the mechanism by which one event contributes to the genesis of another. This is obviously a very high level definition, but the goal now is to translate this into a mathematical formula. And that's where the challenge of developing a causal inference method comes into play. But regardless of this, most people will agree with many of the properties that your method should have, even if is not generally agree what should be the exact definition of causality. One very basic property is that the causes should precede the effect in time. So this is the concept of past and future, and that has to be embedded in your system. So the causality flows from the past to the future, but not the other way around. And most people also would agree in what causality is not. Is not association and correlation. And just to give you some examples of what I mean by that. So this is a person who decided to drink a lot. And then because of that, the next day, it went to sleep with the shoes on. But also then after waking up, then the person had a headache. So obviously here, the causation is the drinking. But this person might think that the headache is actually because of sleeping with the shoes on, but we know that's not the case. There is an association. So it happened to be that every time that he drinks, he will sleep with the shoes on, and then will have a headache. But that we know that this is not the actual cause. And this is a particular case that is called a confounder. So we have this variable that is drinking that is affecting to many different things in the future. And the goal is, okay, we would like to be able to detect this type of situations that in this example is obvious, but when you have a system with 1,000 variables, all interacting in a nonlinear way, then it might not be so obvious if these things are happening. The other concept is the correlation that people are more familiar with. Essentially, we know that correlation doesn't imply causation, so two variables might be correlated. But that doesn't mean there is causality. This is particularly important if you want to manipulate your system. If I want to manipulate this system, I might think that this guy on top of the track is actually the one that is pushing the track. So now I want to move this track faster. So maybe I tell this guy, push harder. But it's true that there is a correlation, but that's not going to work. I need to identify correctly that the guy who is pushing this track is the other one guy on the rear part of the track, and that's the one I need to tell go faster or slower if I want to control what this track is doing. This is another example. This is a bit more silly, but typically I like to show this one. It's another example of confounder. So this is as a function of the year, the number of degrees awarded in sociology doctorates, and also the non-commercial space launches. And actually things that tend to correlate very well. So you can work to compute correlations like 80% or above correlation. And that correlation is true. I mean, they are actually correlated. But it's clear that there is no causation. There is another variable that is actually causing this. So maybe the economy is going well, and that's affecting many aspects of the social life of people, including this. So we would like to detect these things that are correlated, but actually there is no cause and effect between them. So the last, that's related to this second bullet point. And the last one, I wouldn't say is like a universally agreed property, but it's a property that that we adopt, at least in my framework, and other people also do, that is the way of understanding causality as an emergent property rather than something intrinsic to the equations that we are solving. And let me give you an example of what I mean by that. I borrow this from minute physics. This is a cup that you have coffee and milk, and if you wait in time, there is some stirring here happening, so things are mixing, so now suddenly everything is mixed, the coffee and the milk. And this is what we expect to see. But how about I show you this other system in which I have coffee and milk and both mixed together, and suddenly they unmixed, and now I have the milk and the coffee. So this system, there is nothing in the law of physics that forbids this to happen. So this system, both of them, the one that I show you moving forward and backwards, they both comply with conservation of energy, mass, and momentum. So in principle, in the law of physics, according to them, both are possible. But we know that this is not going to happen. It's a matter of probabilities. And probably you are familiar with what you heard about before, the concept of entropy. So the system is moving in the direction of higher entropy, and that means that the things will tend to mix, but it's very highly improbable, although not impossible, that they will unmix. So this idea is already hinting at causality and the arrow of time related to entropy, and entropy has to do with uncertainty in a way. And uncertainty is just a different way of talking about information. And that will connect later with the definition that we use for causality that is based on information. But in generally, going back to this, following this example, one way of understanding causality, considering that many laws in physics are reversible, I can switch the sign of the time and they work exactly the same. So it seems to be that causality is not so meaningful in those cases, because the reverse pattern is also possible. But we can think of causality as an emergent property. So we have some coarse graining of the system. We don't know all the details. I don't know how all the molecules are moving. And because of that, I lose some information. And because of that, it gives me the illusion of time moving forward, and also the illusion of causality. This example, this is the Lorenz attractor. It's just a dynamical system where it depends on three components, X, Y, Z, and this is what the system is moving around in this butterfly. So in principle, if you tell me all these three components, at least for a short time, I'll be able to tell very well what is going to happen. That's okay. However, if suddenly I lose information from one component, now one component is microscopic from my point of view, then I will only see a two-dimensional version. And now I cannot tell what is going to happen all the time. And this is why Weiner kind of try to formalize a bit more the concept of causality. So one event is causal to another one if the information in one event improves the knowledge of the other one. And this was useful in a way to make more concrete the definition of causality. Again, we need to now translate this into a mathematical formula.
So question about this definition, because correlation fits this notion, knowing what that you want to see with shoes on does allow you to predict your headache.
Yes, that's true.
Knowledge is a squiggly word that I don't know what it means.
Yeah, so in a way, predictability is related to correlation. So if you just want to predict, correlation should be enough. And that's true. But I'll try to argue a bit later how information goes a bit beyond correlation. So two things might be correlated, but that doesn't mean they share any information. That's something that you could detect in a way through how the information flows from one variable to another. In a way, this is still very vague, but I'll try to make it a bit more concrete later.
Excellent.
Yeah. So what are the challenges on causal inference? Again, we are thinking of, we need to develop this method, what we would like our method to do. So these are, I'm going to discuss, there are many, these are the ones that I consider relevant, at least for the problems I care about. So, but I'll try to also give them like, or discuss them in a conceptual way. So we have, I'm going to be working with these three variables, Q1, Q, and 3. So the first type of interaction, so these are like a fundamental interactions in a system, we could have what is called a mediator. So there is an effect between Q3 and Q1, but it happens through another variable. That variable is the mediator. So these Q1 and Q3, they are correlated, but actually the causality doesn't flow directly, it goes through another variable. An example is you have a good education level that would improve your job skills and that will increase your income. But maybe you have a very good education level, but for some reason that doesn't translate into your job skills, so then your income doesn't go up. Another example is the confounder. So this connects with the previous examples I was showing. So there is rainy season, and because of that, the umbrella sales go up, but also the raincoats go up. But we know that there's another variable that is causing that. This happens a lot in systems that are nonlinear. So one variable will be responsible for creating many different effects because of the way it's interacting. So it is important to know that this will happen. And this is also important to detect to avoid the spurious causality between 1 and 2. So because they are highly correlated, but obviously if I try to change Q1 and manipulate that, it's not going to be reflected in Q2 because there is no direct causal link between them. The other one is the collider. There are two types of collider. One is the synergistic. In this case, what happens is that you need two variables acting at the same time of another variable for something to happen. A typical example could be, I have one drug A, and I give it to the patient, and there's no recovery. I try another drug B, I give it to the patient, and there's no recovery. However, if I combine both of them, they recover. So this is a synergy. I need both of them. So in a way, there is causality between these two variables, Q3 and Q2, but in a synergistic way. Individually, they don't produce the effect, but combined they do. This also might happen a lot in many systems. You need to satisfy some conditions for something to happen. If one of those conditions is missing, then you don't see the effect. The last one is similar, but in the opposite direction, is redundant. Because sometimes the variable is not like you need them combined together for something to happen, is that all of them individually are contributing to the same effect. For example, you have a student that is smart, and because of that, the student is getting good grades. That's already enough to get good grades. However, it also happened that the student is very hardworking. And actually being hardworking is also enough to get good grades. So you need both of them. This is also relevant in many systems because you might detect like, well, the cause of this variable Q1 is Q2, but you don't detect that it's a redundancy. So now if you don't want an effect to happen in Q1, what you will say, okay, let's block this variable Q2, but the still effect keeps happening. And that's because there is redundancy. There are other variables that are also creating the same effect. So that was important to detect that. So if I want to get rid of an effect in Q1, I need to block all the variables that are contributing to that effect, not only one of them that I was able to detect. There is also self-causation that is a cause to the variable itself in the future. So the method should be able to detect that. There might be noise. So the noise, I'm representing the art here with W. So noise is essentially a variable that I don't have. So typically, I'm going to be assuming that these Q variables, I have access to them, I can measure them or obtain them from the simulation. But the noise is one of the factors that are affecting. So in a way, the method should be reliable to that. These links, didn't mention about them, but the key idea is that they can be linear, but also non-linear dependence, and that might pose some problems for some methods. And maybe there are other variables. I could measure them or maybe not. They are actually variables that they play a dynamic role in our system, but I don't have them. But ideally, I would also like to know that I'm missing something there. So there are these factors there that are controlling and affecting the causality of this system, and they're external, they are hidden. So I should have a way of quantifying the effect of hidden variables. if any. Okay. So that's kind of the challenges, and this is what we would like to our method to handle. So what are the different methods? I'm going to start with how to define a method for causality. I'm going to start with this concept of causality with interventions. And the reason for this is because it's a very intuitive way of thinking about causality. And it's very simple. The premise, I have a system, I modify the system. That means I introduce an intervention, and then I observe the consequences. An intervention doesn't need to be small. In a way, it's not just a perturbation. It could be actually a very large modification of the system. It's up to me to decide what is the intervention that is meaningful. And then look if something happens. And this is something that most people like a lot in the way of defining causality. There are a few challenges with this definition. One is that sometimes intervention may be impossible. For example, imagine I want to understand the causality between different agents in the stock market in 2008, and I want to understand why the crash affected the stock market. Well, I cannot introduce an intervention. The system is in the past, and even if it was happening right now, how am I going to intervene in that system? Sometimes it's more than that, is that even if I could, I need to manipulate a living organism, or I need to alter the environment. Let's think about, you want to understand how some signals between neurons are propagating and they relate in the brain. So that might imply intervene in the brain of a human person. So that might be something that you don't want to do, for example. But another one that is conceptually more important for dynamical systems is that when you introduce an intervention, usually the dynamical systems, they tend to be around what is called an attractor. So they don't do, not everything is possible, not everything is happening at some point. They tend to do follow a pattern and remain close to that attractor. And if you introduce an intervention, suddenly you are forcing your system to do something that is unexpected, and it will never happen unless you intervene. And then sometimes if you extract a conclusion from there, it could be misleading. And it also implies that you need to decide what kind of intervention you do. So there are sometimes many ways of intervening in the system. It's not clear which one is the best. I have this example to illustrate causality with interventions, how it could be sometimes challenging. So this is Alexander the Great. There was this battle of Gaugamela, and this is it was painted by Courtois. So it would be victorious. So in this battle, so Alexander the Great was leading, and I want to know actually if the reason why they won the battle is because Alexander the Great. I mean, because he's a mastermind of war, and then actually the strategy was the best possible. And let's assume that I can even go back to the past and introduce an intervention. But think about this intervention. I decide that I'm going to take the left arm of Alexander the Great and I'm going to cut it. And imagine that because of that, then Alexander the Great doesn't win this battle anymore. So according to an intervention, if I stick to that approach and I commit 100% to it, my conclusion is that the left arm of Alexander the Great is the cause for the victory of the Battle of Gaugamela. That is a bit weird conclusion, to be honest. So even he wasn't even left-handed. So how do I interpret that? So this case that is obviously a bit ridiculous and, to be honest, a bit extreme, but I think it captured the essence that this definition based on interventions that feels very natural might lead to conclusions that are misleading, and we have to be careful about it. I don't mean it's not useful. I mean, it's very useful in some conditions, but you also need to be careful. What happened here? Well, who knows what happened? Maybe after we cut the arm, he got depressed, or he was sick for a long time. He couldn't talk to the other generals. Who knows? There are so many factors in between that, and I don't know if one of those are actually the key. So this is kind of a caveat that you need to take into account with intervention. So because of this, many people have looked into what is called observational methods. So these are methods, and we don't touch the system, either we don't pan or we don't want to. We just want to look at the system. We just look at the system and we try to infer the causality. In a way, these methods are trying to do, if I just look at the system for a long time, what can I tell about the causal relationships in the system? And this is an overview. I compiled some of the methods. There are actually many methods, so I apologize if this list is not so comprehensive. There are several reviews by Pearl, Campbell, Runge. I really recommend to go to those. They have tables with many methods and the properties, so those are actually wonderful references. Here I'm just providing some classification that I like, in a way, that I created myself, of how different methods work. And one of the methods are based on forecasting. This is the original idea of Granger. So causality in those methods is defined based on, can I predict the future of one variable given other variables in the past? And that method is nice, it's very useful, but as we know, it's somehow relying on correlation. So it's very prone to spurious relationships in that case. Other methods are based on just statistical independence. These methods, typically, they construct a graph. All the variables are connecting with all the variables, and they try to remove links in the graph. How do you remove a link? Well, you test for statistical independence. And if two nodes of the graph are independent, you remove the link, and you are pruning the graph until only the skeleton remains. There are also the one of randomized experiments. This is the one that was related to the Nobel Prize, is potential outcomes. And many of the methods, the ones that I work with, but also many other people work with them before, is the ones based on information theory. Probably the most popular one of the first ones, is the transfer entropy by Shaber, 2000. But there has been other related definitions based on information, including some of myself that I eventually dropped because I didn't like them anymore, and I tried to improve on top of that. One of the methods I'll explain briefly later are related to this information theoretic approach. And other methods are based on reconstructing an attractor. So they are more coming from the point of dynamical systems. They are based on what is called the Takens embedding theorem, that it will tell you that if you look at many past observations in a system for some time, you might be able to reconstruct the attractor exactly, and that is used to introduce a definition of causality. And probably the most popular one, or the original implementation of this idea, is called convergence cross-mapping. I mentioned also some of these methods because I'll briefly compare later my new method with many of these that are here. Okay. So this is an overview. Again, go back to these reviews. They are very nice to really explain what these methods are, pros and cons. The method I'm going to be talking today is the Synergistic-Unique-Redundant decomposition of causality. And the motivation behind this method comes from these challenges that I explained to you before. We realize that if you don't separate or identify these redundant and synergistic components in the causality, similar to these examples that I was providing before, your method tends to get confused. In a way, there is like a double counting of causality, that it will show up in different places, but actually that's not true, it's spurious. So by doing this, we were trying to mitigate that effect as much as possible. And it turned out that helped us to make better predictions in terms of the causality map. So there is a bit of math about the method, but actually not much. I'm going to also keep it very conceptual. Here, I'm just going to introduce the variables. If you want to know more the mathematical background of the method, you can go to the Martinez et al. Paper. But ideally, we have some time series, and these are observations, and these are our Q vector from 1 to n, and n is up to us. We need to choose what are the quantities of interest we care about. For example, it could be temperature and pressure for us, but other people might care about the human heart rate, blood pressure. But the goal, in a way, is that I have a variable in the future. One of these, j, could be any of them, and the plus means in the future. And I want to know the causality from this component to this variable in the future. And the future is here, this delta t. And delta t is also an outcome of the method. So what is the delta t? What is the time horizon where causality happens? And you could actually also extract that as a function of this delta t. So the method is based on two ideas. The method is called SURD because of this synergistic-unique-redundant decomposition. And the first idea is that causality is defined as increasing information. So that's the first strong assumption in this method, is that every time I'm referring to causality, in a way I'm talking about how much information is transferred from one variable to another, the one in the future. So this information, this notion of information, the way we implement that is using the Shannon entropy. So the Shannon entropy, it's a way of quantifying the information in a variable, literally like gigabytes, like how many gigabytes are in this variable and how many gigabytes are transferring from this variable to another one in the future. That's just the way of defining information. And then we need to write down an equation where information shows up. And we apply this principle of forward-in-time propagation of information. That probably is not very controversial. It means just that we're assuming that information can only propagate to the future. And that's it. So by combining these two, I can write this equation. This is my only equation here in this talk. I'm just writing in what you have on the top, just using an equation with entropy. H is entropy here. So information in this variable in the future is equal to all the information that is coming from the past. So if I know all the information from the past, I would be able to explain with absolutely no uncertainty what is happening to a variable. Typically, I don't have all the information from the past. I'm missing variables, and that goes to this last term. So there is the part that I know. The part that I know, I decompose that into redundant, unique, and synergistic causality. And whatever remains is what is called the causality leakage, or just for short, leak. This will quantify the causality that is hidden in a way. And all this is represented with these deltas I, because these are increments of information. And I'm trying to see how that information will propagate to the variable. So now the next question is, how do I compute these increments? There are many of them. This is a sum for many combinations. It depends on how many variables are you looking at in your system. I'm going to give you an schematic of how these different increments are computed. This diagram essentially showing that equation, but visually. That equation that is, I'm writing down here again, it contains all the information in my system is contained in this circle. So that's the information I wanna look at, where that information is coming from the past. And there is a way of breaking this down into different components. You can even almost geometrically in a way do it. And it contains this gray area here where different variables overlap. In this example, I have three variables, the variable Q1, Q2, and Q3. I'm looking at the future of one of them, J, doesn't matter which one. So the gray area is the redundancy. So this is causality that is common to all the variables. And I can extract that, but these overlap. Then there is unique causality that is in red. So this is the causality from a variable that doesn't come from any other individual variable. And then I have synergistic causality. So this is information that I gain when I look at multiple variables at the same time. So suddenly I assume I don't know only one variable 1 and 2, I know both of them at the same time. And that will give you some extra information. And those are the synergies. So it's coming from the joint effect. Then whatever remains to complete the information that I have in the future, that has to come from unobserved variables. And by doing this, you can actually find a closed formula for all these terms, like a mathematical formula for all these terms. And that formula is essentially coming from this diagram, like the way you break down this information into different pieces. It will give you this formula. So that's conceptually what you need to do. And that formula can be evaluated. All the terms can be computed in that formula, including this leak that we are missing of information. Okay, so that's the method. And I'm going to show you how it looks in very simple examples. Before that, let me give you this short summary of other methods. So I try to mention a few methods. There are actually many, but some of the most popular ones are the ones that I decided to put here. And I also try to summarize in a very short sentence what is the essence of each method. That is kind of a bit challenging. So this might not be 100% accurate. Probably you will need to refer back to these works to really see the definition. But at least I tried to summarize it as best as I could. So there is the Granger causality that is based on how much a variable can predict another one, and is based on using a linear model. There is the transfer entropy. It's very similar to the definition that we use because it also uses information. But maybe you can think of this most in terms of uncertainty, of how much knowing one variable will reduce the uncertainty of another variable. And there is the CCM, that is reconstructing the manifold of one variable to see in the past of the other. And the last one is the PCMCI, is doing a test, is testing the null hypothesis, like independent variables, given some parents in a graph. So these methods, I'm listing here some properties of when they apply or they don't apply. If they apply to a collection of variables that is larger than 2, some methods they don't. If they intrinsically can account for nonlinear relationships, stochasticity, adding that noise, it will break the system or not. This is contemporaneous mean, self-causation, and the leak, if they can actually account for whatever is missing. If they can include different time delays into the formulation, or the self-causation. So in a way, some methods are successful and some of the things, the way we design our method is such that it's consistent with all these properties. But I want to emphasize that that's the case by construction because these are the properties we care about. Might be that people who develop these methods, they don't care about these properties. That's one comment about this. The other comment is that there might be other properties that our method don't satisfy. So I don't imply at all that these are the properties you must satisfy. I mean that these are the ones I care about for my typical problems. But there might be other property here. I didn't list that. Our method might not perform well in that case. It's just that that property, I don't know exactly what it is, but there might be one, just to be clear. So our method in a way is going to be then based on these increments of information that is transferred over variables. So if you look at the manuscript I referred to where we developed the method, what we did was to run this method across many test cases and compare with these other methods. And here there is a list of them, but we have over more than 30 cases. And these are cases where we already have an expectation of what should happen with the causality. So we don't know exactly what the value of the causality must be. That's a bit tricky, but at least we know what the causality shouldn't be. And that's very clear in these cases. So we just want to make sure that our model is not going to give us a spurious causality, because that's very clear. And our model is not going to miss a very clear causal link. And that's how we are benchmarking the model and comparing to other methods. And in this case, we were able to successfully go across all these tests and battery of the benchmarks, being consistent with what we expect to be causality in all these cases. Similar to what I mentioned before, that doesn't mean the SURD method will always work. There might be another case that we don't know yet, and we test SURD in that case, and it might break. Actually, it would be very interesting to know what is that case, because we might learn more about our method by looking at that case. I'll show you one simple example. Very simple, the confounder variable. This, I manufactured the example myself, and I use this just to show what is the outcome of what you get from applying the SURD causality. So this is a system with 3 variables. The confounder is the one that is affecting Q1 and Q2, but there is also some self-causation. And in this case, I'm just showing what is the causality to Q1. These are the equations of the system. There is some noise. So SURD will give you something like this. It will give you first redundant causality. So in this case, there is no redundant causality. It will also tell you unique causalities. In this case, it's detecting that the variable 1 is self-causal, because all these causalities here are Q1, and this is coming from, this is the way of reading it, U is unique, and 1 is from where it's coming from. So this is affecting 1. And then there's a synergy between these 2 variables. So it's saying that the synergy between 1 and 3 is enough to know the outcome about the future of Q1, and there is only one synergy. And as you can see here, there was no causality from 1 to 2. So the method didn't pick that up, even if they are correlated. The next quantity that is interesting is whatever we are missing, that is the causality link. And we can also quantify that. And that's shown on the very right. It can go from 0 to 1. And this case is something like 10, 20%. So there is actually something missing, and that can be seen very simply from the equation, because we have some noise. And the noise is a variable that we don't know. So it means that according to this analysis, we don't know exactly the future of Q1 because we are missing the noise. By tweaking this noise, we can show that this causality leak can go up or down. That's why we also use this example to see that that's consistent. If I increase the level of noise, then I could see that how this will go up. And another thing that is nice about the method, because it comes from an equation, I can always scale and normalize things such that they go from 0 to 1, and there are no negative values by constructions. Other methods might give you a negative causality that is actually kind of a weird concept. But that's guaranteed not to happen here. So all these plots, when I sum all the causalities in this plot, they must add to 1. And when I look at the causality leak, it should go also from 0 to 1. In the case of 1, it means that I essentially have no idea what is happening in my system. Another very simple example, this is the collider. We have two variables that are absolutely redundant. They are essentially the same variable, and they're affecting Q1. So the map that you will get is something like this. The first thing are the redundancies, and the first one is the redundancy between the three variables. So all these variables, they have some redundant information, and that's because of this redundancy and the self-causation. All of them contain the same information about the future of Q1. Then we detect the redundancy between 2 and 3 that will be reflected here. And then there is a synergy between 1 and 2. And that synergy, it comes actually from this equation. So this, and the reason why we detect 1 and 2 and not 1 and 3 is because they are the same, and there is no double counting in this approach. So we will detect this synergy between 1 and 2, but we know that 2 and 3 are also redundant. So in a way, we know that these two variables, they share some information. And then again, the leak is coming from this noise. So there is we are missing something in the system.
The question, how are you defining redundancy? Because I'm trying to differentiate redundancy versus synergy, and it feels like it's the function causing is it kind of the shape, is it that one can go away and the other one stays, whether it's like a sharp peak where it really like they bifurcate very easily, like a hyperbolic versus elliptical differential equation kind of flavor. Is that a good analogy?
I don't know actually if there is a rigorous connection between whether the hyperbolicity of an equation or not and what we get here. The way I would interpret this, it would be purely in terms of information, or in terms of what this is telling me is that sometimes all these variables Q and Q, they contain the same information about the future of the variable 1. And sometimes I actually need to know at the same time the variable 1 and 2 to know what is going to happen to the future. Now, whether that might be connected to some properties of the equation, that's a very interesting question. I really don't know the answer, but it could be that it is related, because in a way, the way the information propagates in the equation, it has to be connected by how the equation is constructed and how are the interactions defined in the equation. So there must be a connection somehow, although I really wouldn't know rigorously what are the conditions in which that relationship can be established.
Right, and because I'm trying to understand what do you do with this differentiation? Because it's an important one, but concretely what it means, it feels like it could be that they're in fact correlated because they have a common cause. In fact, maybe what I'm trying to get at is how do you differentiate them having a common cause, therefore common information, therefore they're redundant, versus it doesn't matter what one of them is because they co-dampen each other in the subsequent dynamics.
Yeah, I mean, this is essentially what this map is telling you. It's telling you that sometimes you don't need the variable 2 and 3 at the same time. You just need 1. You need either 2 or either 3, and that is giving you the same information about what is going to happen in the future. But that's not enough. Sometimes you need to know 1 and 2 at the same time. If you don't know both of them simultaneously, then you cannot reduce the uncertainty about the future. Maybe that's one way of thinking about it. It's about how much uncertainty you have in the future. If you don't know anything about your system, you don't know any variable, you have 100% uncertainty about the future. Now, if I give you the variable Q2 and Q3, well, sometimes you just need one of them, either 2 or either 3. Many times you don't need both of them at the same time. But if you really want to know even more about the future, then you need to know variable 1 in combination with one of the previous ones, like 2. And that's how you build up, in a way, how adding different variables to your knowledge are helping you to understand what is going to happen in the system. In a way, this is the interpretation of of the method itself. It's an interpretation because the method is constructed to mean that.
Okay, so it sounds like this seems to have a lot of the same flavor as the PC algorithm, but whereas they and the PCMCI they focus on correlation as the notion of information, whereas you using channel entropy. Is that fair? And how are these metrics different?
Let's go back to this.
Yeah.
So this is the test cases that we tested, including PCMCI. Yeah. I'm going to tell you, PCMCI is based on testing the null hypothesis of statistical independence.
Yeah.
PCMCI can be implemented in many different ways. Can be implemented using correlations, nonlinear correlations, like a parkour, or could be implemented using information like the mutual information. So you also have a flavor in that way. But what the PCMCI does not do is decomposing the causality into redundant and synergistic. And because it cannot tell the difference between redundant and synergistic, that causality will mess up. I will be double counted in different interactions. That's why sometimes it will give you misleading answers and causal links. So in a way, the key is not so much information, because other methods can also implement information. Transfer entropy is based on information. PCMCI can also be based on information. The key here that enables these methods, I would say, to provide causal relationships that are more consistent with what we expect is because of the synergistic and redundant decomposition. That's really the key, and that's really the difference with other methods.
So, okay, so is maybe the big trick that you're playing, whereas a lot of these methods look at triples, like one or two causes and one effect. You do more permutations of possible causes, so you can differentiate which combinations are, synergistic or redundant, which ones are independent.
Yeah, I mean, you could definitely change the flavor of many of these methods to introduce different combinations and try to introduce a definition of redundant and synergistic in a way that will compensate for that. I'm sure that also people have been looking into that and how to do that, or a different version, even if it's not called redundant and synergy. And I think that that's fair. I think that what I like of our method is that by construction is conservative. So when I sum everything together, I get 1. And that guarantees. It's not only that so the first component that is important is decomposing synergy and redundancy and unique. The second component is very important, is that it comes from an equation that has to be satisfied. So when I add all my causalities together, I get 100%. So there is no double counting. It's very clear if a causality is weak or strong, and it's very clear if I'm missing something or not. And that comes from this map here. That wouldn't happen with PCMCI, for example. The sum of all the causalities has no meaning. But here, the sum of all causalities is constrained by the propagation of information equation. And that's a very strong constraint. And I think that also includes nice properties into the method. That being said, there are also advantages of PCMCI, to be honest. I think PCMCI, it would scale very well when the number of variables is huge. And our method, for example, would probably struggle in that case. If you have 100 variables, PCMCI would be probably the way to go. Would be more meaningful. In our case, if we have many variables, let's say more than 10, then you need to start to be very careful about, because you might not have enough data. So I mean, not everything is perfect in a way in this method. I don't want to imply that, of course.
So for you, it's multiple hypothesis testing. That would be because you have many more hypotheses to test. Well, your hypothesis.
You can think in that way, yeah. You can think of this as, in a way, I'm testing much more hypotheses in different combinations, but I'm testing the hypothesis under some constraints. And my constraints, if I go back to the method itself, it comes from this. I mean, I'm constraining my terms to satisfy this equation and to this breakdown to follow this schematic that also has very nice properties in terms of additivity of these information increments and how they behave. So it's some test hypothesis under some constraints. But I think that that's also a fair way of looking at it, yeah.
Got it. Thank you.
I was talking about these different applications. I know I don't have a lot of time, but I wanted to also show one very simple case of of physical insight. So I'm going to talk about this, how we can test this in a real case that we want to understand what is happening. For that, I have this case. This is a simulation. This is water. This is liquid. And the top is the wind blowing, and then it will generate some waves. And this problem has been looked at in many different ways. It has been looked without having a solid surface. It has been looking at the sea, the waves, and many different ways. But the idea is always that you can measure this U is velocity, inner is very close to the surface, and you can measure also outer that is farther away. And these are the signals. Typically, people will measure these experimentally, so that you will get some experiments and measure close to the surface and in the outer part. And the idea is that, so these outer motions are shaping they have a imprint on the surface, and they will generate some particular waves. But those waves actually there's no feedback back to the outer. That's one of the hypotheses, and that's called the top-down interaction. So the outer part will affect the surface of the ocean, but not the other way around. But there is also the alternative hypothesis that some people will argue about, that is that bottom up. So those waves, they will feed back to the motions of the air. So this is something we wanted to test using our causality method. It has also been tested using other approaches. So we took these velocity signals and they were experimentally measured. And we apply our SURD method, causality from outer to inner and from inner to outer. And here we have the redundant causality, the unique from the outer, the unique from the inner, and the synergistic. And the idea is that here, the unique from this variable inner, so there is no causality at all here. So not either to itself or to the outer part. The conclusion here, right, obviously this is, the discussion is a bit longer than this. I'm just trying to capture the essence of this problem here. This will validate the hypothesis that the interactions are top-down. So just a very simple example of if you have different hypotheses of how things are interacting in your system, then you can use this tool to try to, in a way, falsify some of those hypotheses. That's one way of thinking about this. That's essentially everything I wanted to tell you about the method and applications. I also would like to mention a few limitations of the method. The first one, I wouldn't say it's a limitation, maybe it's just a common sense, but obviously this method, SURD, as any other methods, is just a tool. And it might help you to get the correct answer, but obviously you need to pose the correct questions. What are the variables you are looking at? Why are you looking at them? What do they mean? Are you missing things that are key? Is your physical hypothesis that you are posing, is that meaningful or not? So usually that's the most important part of the problem. And once that's very clearly defined and is meaningful, then you can come up with our method SURD, or sometimes maybe other methods if you think that they are more appropriate for your problem, and then try to answer that question. The other idea is that this is a kind of a probabilistic view of causality. We have chaotic systems, and we could also define a deterministic causality that connects to these laws of physics that they could be reversed on time. That's why it's a bit controversial, causality in those cases. But again, this is one approach. It's probabilistic and it's observational. So we need to also work within that framework and interpret the results within that framework. And because of that, it's only applicable to variables. So if there is something in your problem that is constant, and it's a parameter and of the system and it doesn't change. So in a way, by definition, causality has to do with changing in time. If something doesn't change in time ever, then there is no causality. So some problems, you could artificially change a parameter, but that doesn't mean in reality it's going to change. So you also need to take that into account. And the other point, I touched on that a bit, this method requires to reconstruct probability distributions in high dimensions. So that tends to be data hungry, to be very demanding in some cases. So you might need a lot of samples to get meaningful results. It depends on how many variables are you looking at, but it could be 1,000, 10,000, 100,000, millions of samples, billions of samples. It depends on the problem. So some people would consider this a strong weakness. I think it is in a way. Other people will argue that we are in the age of data, so maybe it's not so bad. And also, as a comment, so the method has very nice properties, but again, if you don't pose the correct question and you are missing key variables that they're very important for your system, then many of these properties are going to be lost and broken. Hopefully, in this method, we try to mitigate that by the causality leak. That is something that other methods don't have. The causality leak is a safeguard mechanism in our method to detect when you are applying your method to a set of variables that are not enough. You are missing something important. Other methods don't have that. And I think that that's something very useful to this. So that was all. I'm using this as a summary of how causal inference might be very useful to understand systems, to create models, control, and I've presented a method that is well suited for the cases and problems that we care about in my group, the SURD method, and I hope that it also gave you a flavor of the type of applications. I have other applications related to reducer the model and control that are very interesting, but I didn't have time to talk about those. But if you're interested, yes, you can go to my website and look into our work, or just reach out to me. So that's it.
Well, thank you very much. It's fascinating. Let me just ask one final question. Just brought up by the Alexander story, because a lot of it can be decomposed. I'm actually noticing a bunch of synergistic-redundant confounders between his various limbs. But if you start saying like there's a kind of a synergy among the limbs, you kind of need them all to function in order for him to like fight in battle. But if you give him like 5 arms, not so much. It feels redundant.
Yeah,
which kind of indicates there's a flavor of causality which are state dependent in some way. It's not a variable is redundant or synergistic or pair. It depends on their values. So to what extent is that a challenge and like opportunity?
Yeah, I think that example I think is very revealing in a way of that there is, I would say, a lot of work to be done. There is a lot of work in interventions, to be honest. And what are the optimal interventions? How do you intervene the system? So I want to acknowledge first that there's a lot of work on that. But what I typically try to emphasize with that example is that how important is that? How important is to know what you are doing in the system, and when the system is very complex, like human life and interaction between humans and what happens, that becomes actually extremely important. And there is opportunities, I would say. I would say that as an opportunity. I like a lot the idea of intervention, and I would like to have a working definition in causality based on intervention that will help me to understand the system well. At the same time, I want to avoid getting these misleading conclusions, like manipulating a part of the system and then things change completely, or the other way around. I have other examples I didn't mention here where it's the opposite. There is a clear causal link between two things, and introduce an intervention and nothing happens. So your conclusion might be that things don't matter. So you can create examples in one way or the other. But I think there's an opportunity. I'm personally also very interested in understanding the connection between interventions, interventional causality and observational causality, and also extensions of interventional causality accounting for synergistic and redundant interactions. So they might help us understand better what is going on.
It makes sense. And then just pushing on this, this becomes very relevant in genomic studies where you can intervene ethically at a very large scale. And there you do have exactly this phenomena where you change something and it has no effect. But if you change 10 other things as well, then it does have an effect.
Yeah.
It does seem like a study of a combinatorial experimental design. That's really what you're pointing at, that you have to sample that space sparsely.
Yeah. And also to be clear, I gave an example where interventions might be a bit challenging to interpret, but there are other cases with other systems where intervention has a very clear interpretation, and they are very useful. So that also happens. In a way, it depends on the problem.
Yeah. Well, that makes a lot of sense. Thank you very much. It was fascinating.
Yeah, thanks a lot for the opportunity.